All right, so let's continue our discussion. And last lecture we had looked at a differential pair, which is shown over here, which is biased through a resistor here, resistor and the negative supply voltage. So that biases the transistor Q1 and Q2. And the load of this particular differential pair is a resistor again, RC, attached to the collector here. And we had seen these expressions for differential mode gain. ADM was 0.5 GMRC, ACM was GM by 1 plus 2 GMRE RC here. And if we take the ratio of the two, we get a common mode rejection ratio, which is 0.5 plus GMREE here. And if we plug in the values for GM is ICQ by VT, which is nothing but IEE, the current here in this resistor divided by 2 here. And therefore, if we take this GM here and we plug it into this expression, then we get CMRR is 0.5 plus IE times RE by 2 VT here. And we know that drop here, the drop IE times RE here, the drop is nothing but the voltage here is minus 0.7, the voltage here is VEE here. So that's the net drop here divided by 2 VT. So CMRR then depends primarily on the negative supply voltage here. And that decides the CMRR here. And for a fairly large negative supply voltage of 12 that you see here, you can obtain CMRR of only 218 or so. And as I was telling that if you have a smaller supply voltage, then CMRR would be even smaller here. So one of the challenges before us is how do we improve CMRR without requiring very large supply voltages here. All right, so we would like to use maybe 1.5 or even 3 volt and obtain CMRR, which is high. And as I said, what we consider as high, of course, varies from application to application, but we require at least 10 to the power 4 or 10 to the power 5. That's the kind of a number that we are looking for when we can say CMRR is high for this particular amplifier here. And note that since CMRR, if we look at this expression here, it depends on REE here. So if we are trying to improve CMRR, then we should try and replace REE by another element. And we said that one of the things that we can do is replace it by a current source. So we have taken REE out and we have replaced it by a current source. Now this transistor Q3 that you see here, it will be biased in active region. And in active region, we know that the transistor acts as a current source here. And how do we bias Q3? We bias it through Q4 here. And if you recall, in one of the early lectures in a homework assignment, we had seen Q4 and Q3 form a current mirror. Whatever is the current that flows here, the same current almost flows in Q3 as well. And therefore, the current IEE is decided by the current that flows here. And if we look at this side here, the current that flows here, we know that we have VCC at one end of our bias. And at the other end, we have this voltage here, which is same as base voltage. So we know that this voltage is equal to whatever is the negative supply voltage plus 0.7 here. So we know that this voltage here, and we know this voltage here. And therefore, by choosing our bias of a desired value, you can get any current to flow in Q4. And the same current then flows through Q3 here. So that's how you set the current IE. You choose a particular value of R bias, and that decides the current that flows in this particular branch. And so that's how you bias your differential pair without the use of a resistor, but by using transistor itself. Now, if we do that, so bias point analysis is then straightforward. As I said, the voltage at this end is VCC. The voltage at this end is minus 0.7. The voltage here would be, right, so this would be minus VE plus 0.7 here. And therefore, the net drop across the resistor here would be this much divided by R bias. So that gives us IEE here. And so DC or bias point analysis is straightforward. Small signal analysis, note that in small signal analysis, what we have to do is now replace Q3, this one. And we note that, if you look at it from this side, the voltage and all that from here is all DC here, or a bias point. There's no signal which is coming in here, which means that if we look at the base here, the base will be small signal ground. Okay, base will be small signal ground. And then this Q3 with the base as small signal ground, this one is also ground. So when you look at Q3 from the collector side, it appears as nothing but R03, the output resistance here. So that's what we replace this by, R03 here. And R03 we note is early voltage divided by the current, net current that flows through this particular transistor here. So therefore, this transistor Q3 then acts simply as a resistor, R03, with the value VA by IE here. And now all the results remain the same. Note that in the collector we have not changed anything. So differential mode gain, common mode gain, everything remains the same except that wherever REE is there, we replace it by R03 here. So ADM remains the same. Common mode gain, GM by 1 plus 2 GM REE here. So we'll replace REE by R03 here. And similarly, CMRR was ADM by ACM is 0.5 plus GMRE. So we'll replace REE by R03. So everything remains the same except that we have used a transistor here, and the transistor provides us with a large value of R03 here. Okay. Yes. Why what? Directly connect a voltage here? Well, how do you generate a voltage? This is, if you look at it, it is nothing but generating a voltage here. This current that you flow here, it eventually generates a voltage at this particular node, and this voltage is what biases Q3. So it's you can think upon it as a bias circuitry for Q3. You're right. All you need is a voltage at the base. What is Q4? So how do you generate? How do you generate the bias here? See, if I were to apply a direct voltage to the base here, all of you know that the transistor current is very sensitive to base emitter voltage here. It's exponentially dependent here. So I can't simply use a voltage divider and then apply it here. Otherwise, I have to use the arrangement that we use for, arrangement. Here I will have to put R1, R2, and then we'll have to put a resistor here, all of that to make a stable current. So we have to go to that arrangement. The alternative is to use here. So as you can see here, this voltage is pretty well defined because the drop from here to here is reasonably well defined, 0.7 here, and this voltage is here. So this current is well defined. And if this current is well defined and Q4 and Q3 are identical, so the same current ends up flowing. Okay. So in all these, you remember we are trying to make an amplifier on a piece of IC on chip, which we also call as an IC amplifier. So we try and minimize the use of resistors. As much as possible that R1, R2, RE will try and minimize use transistors as much as possible here. So this uses only one single resistor, and using one single resistor, we bias Q3. And similarly, I had shown earlier that if you have an amplifier somewhere else you require a current, then you can use this one here to generate currents for elsewhere in the circuit also. Okay, so one single bias circuitry here, R bias and Q4, and it can provide current not only here, but in other parts of the circuit as well. Okay. So anyway, if you take GM, remember, so GM RE here. So if you take RE out and replace it by R0 here, which is VA by IE here. So what you end up getting is CMRR. I think not shown here. So you end up getting CMRR. If you go back here, you end up getting CMRR, which is nothing but, so IE RE will become VA. It will be early voltage here. So you end up getting CMRR, which is 0.5 early voltage divided by VT. And early voltages, as we recall, for a transistor can be as high as 100 volts. So what you end up getting is CMRR, which is pretty high, and without requiring a supply voltage. It is no longer dependent on VE. Instead of VE, you'll end up getting a early voltage. And so even if you have supply voltages of plus 1.5 or minus 1.5, and if the transistor has an early voltage of 100, you'll keep on getting a high value of CMRR. So that's what this particular replacement of a resistor by a current source, that's the advantage that you get. So differential mode gain remains the same. Common mode gain reduces a lot because RE has become large, and CMRR improves considerably here. If you're not happy with the CMRR that you get, if you want even higher CMRR, what you can do is you can take Q3 and you can connect in series with Q3 another transistor Q4. here Q3, and then you get another transistor Q4. Then when you look from the collector side, you see Q3 along with the Q4, and this resistor that you see here becomes even larger. And therefore, you get even higher values of common mode gain, or CMRR, even lower values of ACM and higher values of CMRR. So you could do that. We'll see it in the context of MOS transistors, MOS amplifiers. The other, so this tells us how to solve the problem of CMRR. What you need to do is replace it by, and note that this current source has a resistance of R03. In the ideal case, suppose you had an ideal current source. If you had an ideal current source, R0 would go to infinity, and therefore your CMRR will go to infinity. So all you need to do to get good values of CMRR is build a very good current source here. Very good current source means very, very high values of output choices here. The better the current source, the lower the ACM and the higher the CMRR. So that's how you solve the problem of getting a large values of CMRR, by building good quality current source at this particular point. Differential mode gain, on the other hand, if you want to build higher values, then what you have to do is replace RC by a active load here. And so this is what we are going to do next. So we replace RC by a PNP transistor. We had seen earlier that if you replace by NPN, it doesn't increase gain. You have to replace it by a PNP here. And so both of them are being replaced by PNP here. RC by Q3 here, PNP transistor, and this RC also by another PNP transistor Q4. And the base, we have to bias Q3 and Q4 in active region here. So we have to apply a voltage here at this particular node in order to bias these two transistors in active mode here. And this particular amplifier has a problem. The problem is, first of all, we require a base voltage, which means that we have to generate a circuit to apply V bias here. Remember, the only supply voltages that enter your IC are VCC and VE here. These will be like two pins in an IC, and you will have VCC and VE going here. So this bias voltage that you see here, you have to generate it from VCC and VE here. So you'll have to use some kind of resistors or whatever in order to generate V bias here. Now the trouble with this particular circuit is that, note that this transistor is in active region and this transistor also is in active region. And in an active region, a transistor acts as a current source, which means that this acts as a current source and this also acts as a current source. And all of you should know, you should never put two current sources in series. Just like you should not put two voltage sources in parallel. If they're identical, then it's fine. But in practice, you will never get two identical voltage sources. If one of them is 1.5 and other one of them is 1.55. If you connect two voltage sources in parallel, one of the sources will fail. The effective voltage across the two nodes will be either 1.5 or 1.5. One of the two sources will fail. Similarly, if you connect two current sources in series, this is a current source and this is a current source. The value of this current will be decided by here, IE, and this current will try to carry a current depending on the voltage that you apply here. And if you have two currents in series here, invariably what would happen is either this one will tend to become a little larger than Q1, or Q1 will become a little larger than Q3. Now obviously you have one single current flowing in this branch here because they're in series. So invariably what happens is one of the transistors goes into saturation region. Either Q3 will go into saturation region or Q1 will go into saturation region. Both of them cannot be in active mode, because to be in active mode, then they are like current sources, and invariably the current sources will be a little different from each other. Okay, so you can go and make, I'll show you this particular circuit in a minute, some simulation results here. Okay, so two problems with this particular amplifier. One is I need to generate V bias, so I need a separate circuit to generate V bias. The other thing is the whole circuit is invariably one or the other transistor will go into saturation region, or even if it doesn't go into saturation region, the whole circuit is extremely sensitive to V bias or to VCC. Extremely sensitive. I'll just show it to you in a minute here. Look at this result. In this case, note that I have this transistor Q1 and Q2. They are biased at 2 milliamperes here, 2 milliamperes, and the bias voltage here there is no connection here. The bias voltage applied to the base is 11.3, assuming that the drop is approximately 0.7, so we have applied 11.3 here. And note that when I apply 11.3, the voltages at this node is 11.87, this is 11.87, which means that this is 12 here, and this is 11.87, which means that the voltage across the transistor is 0.13. 0.13, which means that the transistors are in saturation region. So, I arbitrarily, assuming that the drops are going to be 0.7, so I applied 11.3, so that the drop is 0.7 here, but we find that both these nodes have gone to a very high value here, 11.87 here, and the transistors are in saturation region. And if Q4 and Q3 are in saturation region, then the transistor, this particular one, is not going to amplify. Okay. Now, then let me show you how sensitive it is to this bias voltage here. Suppose I increase, instead of 11.3, I make it 11.31. Okay. Just 10 millivolt difference here. 11.31. Note what happened to the voltages. Go back here, 11.87 here, and just 10 millivolt increase in this voltage here, this has become minus 0.7 here. Almost minus 0.7. Now this is close to minus 0.7. This is also minus 0.7. So what has happened to this transistor? This has gone into saturation region. So this is what I'm trying to tell you is this particular circuit is extremely sensitive. Either this one is going into saturation or this one is going into saturation. Okay. And it's very hard to apply a voltage here such that you can make Q4 and Q1 all biased in active region. It's very difficult. So that's the problem with this particular circuit here. Okay. And so first of all, we require a separate circuit to generate V bias. And the other one is my entire circuit is so sensitive to V bias. And that either this one is going into saturation or this one is going into saturation. Now, a very simple problem, a very simple solution to this particular problem is the following. This is the amplifier that we are talking about, replacing the load by PNP here. A very simple solution that I'm showing you is here. All that we did was, this Q3 and Q4 that you see here, we needed to bias it. We have taken the base here and connected it to the collector of this particular transistor. Okay. Now, all of you will recognize that this transistor Q3 then, with this base and collector shorted together, is like a diode. It's like a diode here, and therefore, let me show you then that it solves a biasing problem. It solves a biasing problem because what happens is, this current IE divides between Q1 and Q2. Okay, Q1 and Q2 are identical, so it divides between these two. This current then, almost like half of this current flows here. As it flows here through Q3, it generates a voltage at the base here. How much voltage is generated at the base? A voltage which would allow a current of, let's say, IE by 2 to flow here. The same voltage then goes to Q4 and causes the current to flow here as well. Okay, so let me show you the results here. So the bias point now is very stable. This point is very stable here because whatever is VCC minus base emitter voltage drop here. So that's this particular point. And this one is also very close to this particular one. Okay, so let me show you the same simulation results. Look at the value here. So I have a differential pair, bias at 2 milliamperes, and this node is 11.3, almost like 0.7 volt drop here, and this node is 10.26 here, and this is also biased in active mode, and this is also biased in active mode. This voltage will not be equal to 11.3, and you can see why, because the currents in these two transistors are a little different here. You can see this is 995.725 here, and this is 986 point here. The currents are a little different here. Note here that the current that flows in Q1, is equal to the collector current of Q3 plus the base current which flows in here. While the current that flows in Q2 is simply the collector current of Q4. Okay, so that's why this current that you see here is a little higher than this particular current here, because the current that flows in is collector of Q3 plus the base current here. Base current flows in from here and joins and flows into Q1 here. Anyway, so I've shown that both the transistors are in active mode. Let me just change the supply voltage just to show you sensitivity. Suppose I change supply voltage to 12.5. Well, the voltages do change, but both are again biased in active mode. So a 0.5 volt change in supply voltage, all that it did was I had 10.26 here and 10.75 here. So it basically changed by 0.5 volts. Whatever is the change in supply voltage here, almost the same change is appearing over here. But the transistors remain in forward active mode. So we have a very stable, reasonably stable bias point here. Both the transistors Q3 and Q4 are biased in forward active mode. So instead of applying a voltage here, a simple short here between base and collector allows us to bias this particular differential amplifier with a fairly stable bias point here, with both transistors working in active mode here. But obviously you can see now that the circuit is no longer symmetrical. This one, base and collector are shorted together. So this one is like a diode and its resistance is very small. On the other hand, base and collector are separate here. The resistance of this particular one, small signal resistance here, would be large here. So what happens is you develop voltage gain here and you don't get much voltage gain here. Because at this particular node, the resistance node that between here and ground will be 1 by GM. Resistance of a diode is basically 1 by GM. So the resistance at this node becomes very small and you hardly get any gain here. While the resistance at this particular node, we'll see in a minute, is high and you get large gain here. So it's an amplifier which is no longer symmetrical, unlike a previous amplifier. It's no longer symmetrical with gain being developed only at this particular point. All right, so let's do the analysis then, small signal analysis of this amplifier here. So small signal analysis is broken into two parts. One is differential mode, where we apply 0.5 VID here and minus 0.5 VID here, differential mode signal. And in common mode, we'll apply VIC here and VIC here. Okay, so the way we do this small signal analysis here is one way, of course, is replace the transistor by small signal model, and you'll have, replace Q1, Q2, Q3, Q4 by the small signal models, and then use your KVL, KCL, whatever you want to use in order to solve and obtain V0. The other way is a method that works and it's, gives us more insight and also allows us to solve circuits with less effort. And that is by, for example, the node at which you are interested in, this node, what you do is you build a Norton's equivalent at that node. You build a Norton's equivalent at that node, meaning that this entire circuit that you see here, this entire circuit will be converted into a Norton's equivalent, which means a Norton's current and a Norton's resistance. So remember, the whole circuit is a linear circuit, and when you look at from this point, this port, the whole circuit can be a Norton's current in parallel with the Norton's resistance. Okay, that's what we'll do. And so the first thing that we try to do is determine Norton's current here. So what we do is we take this particular node and ground it, and whatever is the current flowing in, that's the Norton's current. So we try to determine the Norton's current first. And in that, if we look, and the other thing that we'll do is Norton's current, and the other thing is Norton's resistance here. So we remove the source, remove means short it here, and we try to determine what is the net Norton's resistance here. All right. And once we have that, then the whole circuit is nothing but IN in parallel with RN. And therefore, we can easily determine what is the output voltage. So that's our strategy. Okay. So let's do the first one. How do we determine the Norton's current? And then we'll determine the Norton's resistance. Okay. So Norton's current means we have this node is shorted, small signal ground, and we want to determine this current. Now, in order to do that, we note the following here. This node is ground. And if we look at this particular node here, the corresponding node at this particular point here, we note that this node is connected to ground here through what? Through Q3, whose base and collector are shorted together. So how much is the resistance between this node and ground? 1 by GM. It's a very small resistor. If it's a very small resistor between this point and this point here, 1 by GM, which means that the voltage developed at this particular node will also be very small. If the resistance between this particular node and ground is very small, then whatever current flows through this particular resistor, the voltage at this node also will be very small. Now, if the voltage is very small, to the first order approximation, you can assume that this node is also very close to ground. If you assume that this particular node is also very close to ground, and you look at this circuit below this particular node here, you have Q1, Q2, and you have RO5. You have plus voltage from one side, and you have negative voltage from other side. And then from symmetry, you can assume that this node is ground as well. Okay, so this node is ground, we are saying, and this node is anyway ground. And below this particular line here, the entire circuit is symmetrical with a positive voltage applied on one side and negative voltage applied on the other side, which means that this node is a small signal ground. Okay, so that's why we put this particular node to ground. This node becomes ground, and this node becomes ground here. And this voltage, RO5, disappears. So this is the same argument that we had used earlier when we had a RC here and an RC here. We said that this node becomes a virtual small signal ground. All right, so now we have, so this is, you can simulate and you can show also that this assumption is reasonably accurate, that the voltage at this particular node is like a small signal ground. All right, with this now, let's go forward. Now this transistor here, if you look at Q1 with a voltage 0.5 VID applied here. So this Q1, note that I can replace this Q1 with the voltage applied here by a current source. Remember, when you look at it from the collector side, you see a current source which is GM times V pi, and you see a resistor which is R0. So that's what we have done. When you look at Q1, look at it from the collector side, you see a current source GM, which is GM here, V pi. V pi is nothing but voltage between base and emitter, which is 0.5 VID. So that's where the current is 0.5 GM VID here. And in parallel to it, there's a resistor R0 of Q1. Same thing happens to Q2. Q2 is also, when I look at it, except that the value of the current source will be because the voltage applied is minus 0.5 VID, so it will be minus 0.5 GM VID. And same thing between this node and this node, there'll be a resistor R0. So transistor Q1 and Q2 are replaced by these two elements. Now, if we look at it, this R0 doesn't really matter, as you can see here. Both ends are shorted together, ground and ground, so we can remove it. The other one, if you look at this R0 is between this node and ground. And again, we said between this node and ground here is 1 by GM of this particular transistor. Q3 is nothing but 1 by GM. So 1 by GM is much, much smaller than R0. So there's no need to keep R0 as well. So our circuit then becomes, this R0 of course gets shorted out, and this R0 we have neglected in comparison to the resistor of Q3. So we are left with 0.5 GM VID here, and we are left with minus 0.5 GM VID. All right, so now let's go back here, and then let's look at what is IN. So one contribution to IN you can obviously see is minus 0.5 GM VID. That's obviously IN equal to this much here. The other contribution to IN comes from Q4. And if we look at Q3 and Q4, they look like current mirror. Q3 and Q4 are exactly same transistors. Their base voltage is the same. Their emitter voltage is the same. So whatever is the current flowing in Q3, the same current flows in Q4 as well. So now, with that in mind, note that if this is current flowing in Q3, the same collector current will flow through Q4 also. Because the transistors are identical, their base voltage is the same, their emitter voltage is the same, and so same current flows through Q4. So IN then has a current contribution which is minus 0.5 GM VID, which is here, and there is another current 0.5 GM VID which flows in from here, and that's the other contribution. And so the net current IN then adds up, gives us GM VID. So the net Norton's current is the sum of these two. And note that, as you can see here, minus 0.5 GM VID, which means the current is actually flowing up here, and there's a current coming down from here. The two currents add up and they contribute to IN. And because of the direction of IN, we have minus GM VID. So that's the net Norton's current at this particular point. Okay. Now, these are some of the results that you should keep. I have talked about it, but these are more general results. and it will help you if you memorize this particular results here. A couple of results. One of them says that when you look at a transistor from the collector, and there is a resistor in the base and there's a resistor in the emitter, this is the resistance that you see here. R equal to R naught, 1 plus GM, RE. These are again approximate. Some approximations have been made. So RE parallel RB plus R pi. All right. So what you can do is replace the transistor by its hybrid pi model, apply a voltage Vx, find out the current Ix, divide by Vx by Ix, and verify that the resistor that you get from here follows this particular expression. So that's one. When you look at it from the collector side, when you look at it from the emitter side, we have been saying that the resistor is equal to Rb plus R pi divided by 1 plus beta. A more general expression is here. Rb plus R pi multiplied by Rc plus R naught, Rb plus R pi, Rc plus R naught, beta R naught here. Note that if Rc is small, then what happens is all these terms that you see here, the first 4 terms are negligible compared to the last, which is beta R naught. And so beta R naught comes out, and beta R naught comes out. R naught is much larger than Rc, so you have R naught here. R naught and R naught cancel, and you get your simplified expression, which is Rb plus R pi by beta here. But this is a more general and a more accurate expression. And sometimes what happens is, instead of Rc here, we have another transistor which contributes R0. And in that case, then we cannot neglect some of these values here. So this is more accurate. And similarly, we have an expression for what happens when you look at it from the base side here. Okay, so this is the net resistance when you look at it from the base side. This is from the collector side, and this is from the emitter side here. And another useful result is when you have base and collector shorted together, the net resistance between collector and emitter is simply equal to 1 by Gn. All these results you can easily show through. Conceptually, it's easy to show through small signal analysis, except that for some of these, you have to work out a little and do some simplification in order to arrive at these values here. Okay, so we'll use these results at various places in order to simplify our circuit analysis here. All right, so let's come back now to Norton's resistance here. We have to determine the Norton's resistance at this particular node. The general way of determining resistance always is attach a source Vx, find out what is the current Ix flowing. Now, if we look at this Ix, the Ix has 2 paths. It can flow down here or it can flow up here. Because it's flowing through Q2, we call it Ix2. Because it's flowing through Q4, we call it Ix4 here. And then 1 by Rn will be equal to Ix by Vx here. And Ix we have broken into 2 components, Ix2 and Ix4 here. So what we have to do is determine what is this current Ix2, what is this current Ix4. If we obtain expressions for Ix2 and Ix4, we'll put it here and we'll get the value of Rn. Alright, so now let's look at Ix2. What happens to Ix2 here? Whatever is the current that flows here, this is the collector current, and note that transistor is in active mode, so the emitter current is going to be very close to collector current here. So we'll make that approximation that the current here is also Ix2. Okay, so Ix2 starts from here, goes into the collector, comes out from the emitter. Now it comes here. Once it comes here, it's at an intersection. It can either go down or it can continue to go in the same direction here. Now, how does it decide where to go? Well, it depends on the resistance here. So when it comes here, it sees a resistance here of R05, which is large. And when it looks here, what does it see? Resistance looking into the emitter. And when you look into the emitter, what do you see? If you look into the emitter, go back and see this particular one. If you look into the emitter, and the resistance RC is very small, right? Resistance RC is very small. What you see is basically R pi by beta here. And R pi by beta is what? 1 by Gm. And 1 by Gm is what? 1 by Gm is like very, very small resistor here. Okay, extremely small resistor as compared to this R05. So what happens is, the moment the current arrives here, it sees a large resistance here and sees a small resistance here. So it bypasses R05. It forgets about R05, continues here. Same current flows here. Now it comes here. Now note that this is small signal, so don't worry about the direction of the current here. Okay. So now it comes here, and now, of course, this is the emitter current. So collector current is going to be the same. Okay, emitter and collector currents are the same here. So it continues here. So note that current starts from IX2, starts from here. Eventually, of course, is coming from here, from the source here. Part of it comes here, starts here, goes up here. And then as it comes here, then what happens is between this node and this node here, eventually note that this is nothing but 1 by GM, a resistor, so it flows into the ground. It flows into the ground, so it starts from a source here, goes here, comes back, comes here, and then eventually to the ground here. Okay, so that's how it completes the path. Now, as it arrives here, as I said, between this node and ground, we have a resistor which is 1 by GM. So the voltage that it develops at this node, the voltage is equal to IX2 into 1 by GM3. Because that's the resistance of this particular part. That's the voltage that it develops here. And as I said, this voltage is small. But this voltage also goes into the base of Q4, and we'll see that it has a consequence. It will cause similar current. Whatever current flows in Q3, same current begins to flow in Q4 also. So we'll see that in a minute. So that's the path that IX2 takes here. Okay. But what is the expression for IX2? How do we calculate IX2? So let's do that. If I want to calculate IX2, then note that I've drawn a partial circuit of this to calculate IX2. There's Q2 here. This base is grounded. And we come here. And as I said, looking from here, from this side, this thing is 1 by GM1. So we put 1 by GM1 in parallel with R05. So we'll forget about R05 here. So then what is the value of IX2? IX2 will be equal to Vx divided by the net resistance when you look down here. And the net resistance you can easily show. The resistance IX2 will be equal to Vx, whatever is the voltage you apply here. R02, 1 plus GM into 1 by GM. So here again, basically, is the resistance looking down here at the collector. If you don't want to write it, you can also go back to one of these results here. When you look at from the collector, and note that what was this resistor? 1 by GM. And all this RB plus R pi, so this is R pi here. We don't have any RB. So this is 0, R pi here, and RE is 1 by GM. So 1 by GM is much smaller than R pi, so we forget about R pi. So we get GM into 1 by GM. So this is a factor of 1, and 1 plus 1 is 2. And so the net resistor looking from here is 2R0. Okay, the net resistance looking from the collector is 2R0. So you use this particular result here, and you can write down straight from there that the current that flows here, IX2, will be equal to Vx here, and the net resistor looking into the collector, which is 2R02 here. So that's Vx by 2R02 is the current that goes into the collector of Q2 here. So you can use that particular result of resistance looking into the collector. Okay. Next, let's focus on Q4. Q4, if we come here, then we note that whatever is the voltage that was set up here, which was IX2 into 1 by GM3, the same voltage is going here. Okay. So now let's focus on Q4. Q4 emitter is ground. The base voltage of Q4 is here, IX2 by 1 by GM3, and the collector is over here. And we have applied Vx, and we want to know how much is IX4. So now this is a PNP transistor with a base emitter voltage of how much? VB4. And so what current will flow through Q4? Well, you know that when you look at a transistor from the collector side, you see a current which is GM times the V pi plus the collector voltage divided by R0. So it's nothing but the small signal model of Q4, and except that VB4 we have calculated, which is given here, and R04 is the output resistance of this particular transistor here. So these are the things that you need to know, that from the collector side, when you have a voltage applied to the base, then you get a current source GM4 times VB4 here, the net voltage between the base and emitter, which is VB4, and then this is the output resistance. So what we do is we take VB4 here, we put it here, and then we get a value of IX4, which is equal to IX2 plus Vx by R04. Alright, so we get a value of ix4 and we have an expression for ix2. And now we put them all together. ix2 is Vx by 2R02. ix4 is ix2 plus Vx by R04. 1 by Rn was Ix plus Vx here. So we put both of them together. And finally, we get a very simple result, which is Rn is nothing but a parallel combination of R02 parallel R04. The resistance here of R02 in parallel with R04. Most of the places, in fact, in almost all the textbooks, you will find that what they do, they'll not go through this detailed analysis that we have done. In most of the textbooks, what they would do is, they'll say, well, this is like ground. This is like ground here. And so when you look down, they will take it as ground. When you look down, you see R02. And when you look up, this is also, they will take it as ground. And when you look up, you see R04. And therefore, Rn is simply R02 parallel R04. So most of the places in books, you will find a derivation like that. Very simple. R02 parallel R04, but that's not correct. As I've shown you how the current flows, these nodes are not ground, and how eventually you arrive at a result here. R02, R04, parallel R04. Okay. So the net Norton's resistance then is this output resistance in parallel with this one. Okay. So now we said the net Norton's current is GMVID. The net Norton's resistance is R02 parallel R04. And therefore, your output voltage then will be simply equal to minus IN into Rn, because this whole circuit is a current source in parallel with Rn. So output voltage is minus IN into Rn, and you divide it by VID to get the differential mode gain. And so that's simply equal to GM1 R02 parallel R04. So a fairly simple result finally, but the derivation is involved. Derivation of what is the Norton's current, how it comes about to be GMVID, and what is the Norton's resistance here, R02 parallel R04. Alright, so that's the differential mode gain here. Okay, and note that because R02 and R04 are large quantities, so we'll end up getting a very large differential mode gain. Okay, if you want to know the gain at this particular point, then go back and see that we have already calculated the value at this particular node here is Ix2 by 1 by Gm3. And we have expression for Ix2. Go back and see. Ix2, we have an expression here. Vx by 2R02 here. So you can determine the gain at that particular point. It's embedded in this derivation here. I'm not showing you explicitly. You will find that the gain at this particular point is very close to 1. While the gain at this particular point will be, is a very large quantity. Easily you will get gains, 500,000 because GM and R0 product is very large. So you end up getting a very large differential gain here using this particular stage here. Now, unfortunately, common mode. All right. So before I continue, I want to show you one benefit of this particular stage versus the previous stage here. Remember, we said you can build a differential pair with active load by biasing it from here. And we said that, if this biasing arrangement is not very convenient, it's very sensitive, right? So let's leave that aside for a moment. And suppose I were to do the small signal analysis and find out the gain of this particular stage. What I would find is, I'll not go into the details. What I would find is that the differential mode gain is 0.5 GM R02 parallel R04. You can do the analysis of this particular stage and you'll find it's 0.5 GM R02 parallel R04. Go back and see. This one was giving us GM R02 parallel R04, while this one with the separate bias, it gives you 0.5 GM R02 parallel R04. The gain of this particular stage is half as compared to the stage that we are talking about. All right, so this is fairly easy. If you sit down and you can easily calculate and show this. Common mode analysis is even worse as compared to differential mode. In fact, I don't have an expression for common mode gain, and you'll see in a minute why we don't have an expression here. All right. Okay, so common mode gain means we apply VIC from here, we apply VIC from here. The voltages are the same. This, of course, becomes, we have replaced the current source by output resistance R05. So this is here, and this node becomes small signal ground here. Okay, so we have to analyze this particular stage here. Now note, the circuit is not symmetrical because the voltage at this particular point is not the same as voltage at this particular point. Okay, but many times, all right. So the argument is as follows here. We know that the voltage at this node and the voltage at this node are not going to be the same. Okay, here is a diode connected transistor, and here is a base and collector are not connected together. So V0 is not going to be same as VC1 here. But if we go and look below this particular point here, we see same voltage being applied to the base here. We see transistors Q1 and Q2 identical, and R05 here. So although it's not strictly justified, but we go ahead and make the assumption here that one can still split R05 into two parts and assume that the same current flows in these two transistors here. If you think about Q1 and Q2, why would the current in Q1 and Q2 differ? They have the same base emitter voltage, transistors are identical. Why would the current in Q1 and Q2 differ? Because the collector voltages of the two transistors are not the same. And how does current depend on collector voltage? Through the early effect, 1 plus early VCE divided by VA. So if early voltage is large, to the first order approximation, you can say, well, the collector current is sort of independent of whatever is the voltage at the collector. So therefore, the currents in Q1 and Q2 are going to be identical, and therefore I can do the same splitting of the two of the circuit by splitting it into 2R05, and then we can split the circuit here. All right, so we can split the circuit here, but we can't split it further. Okay. This I can calculate. See, if you look at the left half of the circuit, the left half of the circuit is here. The left half of the circuit is over here. It's not complete actually, but it's reasonably accurate. Why? If you look at this part here, this base and collector are shorted together. So between here and here, I see 1 over GM. But between base and emitter of this one, what do I see? Q4, R pi. Q4 contributes between base and emitter, R pi. And R pi is beta times larger than 1 by GM. So that's why I've neglected the effect of Q4. So Q4, although it's connected here, to the first order approximation, you can forget about Q4. So you're left with this circuit here. Now, if you're left with this circuit is fairly easy to solve because Q3 is nothing but, this one is 1 by GM. And so this is a common source amplifier here with a resistor of 1 by GM and a resistor in the emitter. And we know how to solve this particular part here. So this we can easily calculate. VC1 by VIC here is about 2 GM1 times R05. Note that this will be GM divided by 1 plus GM into the resistor into the emitter node, which is 2R05, multiplied by RC. RC is nothing but 1 by GM3. Okay, so this is the gain that you get here. So this we can get here. But getting this is more difficult here. Okay. So now note that this value that we obtain, the same voltage will go into the base of Q4. So let's look at the right half here. The right half is here. Okay. Now the right half is here. And now what happens is, note what is happening here. What is the phase difference between VC1 and VIC? 180 degree. Right? Note that VC1, there's a negative sign here. So between here and here, there's a 180 degree phase shift here. So this voltage is going here. So between the base and again here, how much will it be? 180 degree here. So what is the net effect of VC1? It tries to develop a voltage which is positive. Right? So it starts from here. If say this is positive, then this is negative here, VIC. And this negative voltage goes here. And this negative will try to develop, make V0 positive. On the other hand, this VIC, what does it try to do? Make V0 negative. And therefore, the two are trying to cancel each other. The two are trying to cancel each other here. This one is going here, negative, and from negative, it tries to make it positive here. And this one tries to make it negative here. And the two are trying to cancel each other. And if we calculate, we've already said what is VC1. And if we calculate, what happens is, using the approximations that we make, this voltage turns out to be 0. The two appear to be cancelling each other exactly. But that's where the problem is, that all these expressions that we have derived, they're all, you can see a big approximate sign there. At various places, we have been making approximations. And after making all those approximations, we find that the output voltage is 0. But it's actually not 0. It's actually not 0. If you don't make the approximations, this and these two do not exactly cancel each other. Now, how do I get an accurate expression of V0, which means that I have to redo the analysis without making any of the approximations? Without making any of the approximations, do an exact analysis, and you'll find V0 will not cancel, and you will get a value for V0 here. But then that's what makes the analysis difficult here. Doing the analysis without making any of those approximations that we've made. So I'll leave that particular problem up to you. Whoever has more patience, maybe go ahead, do the analysis without making any approximation. Exact analysis, do it. I don't have any expression for V0 here. So all that I'm going to leave it is at this stage. Okay, it's not 0. So let me show you an example here. I applied a common mode gain of 0.5 here and 0.5 here. And so this is common mode analysis. The voltage that we get here is 135 microvolts here. And this follows our this one expression here. So when we did the calculation on this side, is pretty accurate, reasonably accurate. I get a value of 130 microvolt, and this gives us 135. While this one, the voltage at this node is minus 4.95 millivolt here. So this voltage is, my simple analysis is telling us that the voltage is 0. And that's because everywhere we've used approximate expression, and therefore it doesn't hold true. And we need a more accurate expression here for common mode gain at this particular point. Okay. And so the common mode gain is 0.01 instead of being 0 according to that. So again, as I said, you have to do a more accurate analysis without making any of the approximations that we have done. And if you do that, obviously you should get the answer here. Now, if we go back to a stage where we had this Q3 and Q4, which were biased through a voltage source here, and we had seen problems with that particular stage here. If we look at common mode gain of that particular stage, we find that the voltage at this particular node is very close to the voltage that we apply here, and common mode gain is much higher here. The common mode gain is close to unity as compared to the differential pair with current mirror load, where the common mode gain is 1 by 100 here. And so this is a summary here. We had calculated the differential mode gain by determining the Norton's current and Norton's resistance. So that's equal to GM1 R02 parallel R04 here. Output resistance at this particular node is R02 parallel R04, which is same as the Norton's resistance here. We don't have an expression for common mode gain. One needs to do a more detailed analysis to obtain the value here. And so in the absence of ACM, we don't have an expression for CMRR as well here. Let's see an example. So in this case, it's bias at 2 milliamperes here, and therefore the 2 milliamperes will divide equally between these two. So we get ICQ1 and ICQ2 as we saw that currents are a little different, but we'll ignore it, assume that they're almost the same, which is 1 milliampere here. So we calculate GM1, R02 of this transistor here, which is same as this one, and R05 is of the current source, and we calculate ADM, which is using the expressions. So one sees the differential mode gain is 2000. There should be actually a positive sign here. There's no phase shift between V0 and Vn. So the differential mode gain is fairly large, which is 2000. RID is 5.2 kilo ohms here. And the common mode gain we have to determine using simulation. We just saw 0.01. And CMRR is pretty high, which is 10 to the power 5 here, 2 times 10 to the power 5, which translates into more than 100 dBs of CMRR here. And therefore, this particular differential pair with current mirror load has very useful properties: large differential gain, very small common mode gain, which translates into very high CMRR here. And This is interesting that this is an amplifier. We had started out by trying to build a differential pair with an active load by connecting a PNP transistor here, biased through this source here, and we had seen that the biasing is very sensitive. And so for this amplifier, besides the biasing, we calculate the differential mode gain. We had seen earlier that it will give us 0.5 GM1 R02 parallel R04 here. And the common mode gain is easier. For this one, we can do a reasonably good calculation here. Common mode gain is here. And if we look at this particular amplifier, where we again have Q3 and Q4, but they're connected in this current mirror fashion here. So it's a current mirror load. And we saw that the bias points are stable. Both transistors are biased in active mode here. And the gain here is twice the gain of this particular part here. And although we don't have an expression, but we showed through simulation that the common mode gain here, for example, simulation showed for one particular design, the gain here was close to 1 and the gain here was 1 by 100 here. So this has all the advantages with respect to this particular one. We don't need a separate bias circuitry, and in addition the bias point is stable. We have twice the gain of this particular one, and we have a common mode gain which is 100 of common mode gain for at least for one particular design as compared to this one. And so this shows that what a single wire can make here. One single connection between base and collector here, and leads to all these very nice advantages here. Stable bias point, double differential gain, much smaller common mode gain, and therefore a much higher CMRR here. So let's stop here.